Hi, my name is Tajana Rushoff, and today I'll be presenting an overview of karst geology and hydrogeology in West Central and North Central Florida. To begin introducing this subject, Florida is home to the highest density of large springs and hundreds of smaller springs in North America. The underwater caves within Florida supply water to those springs. These springs are fed by a limestone aquifer that includes underwater and air-filled caves. This is a karst environment. A karst is a type of topography characterized by solution features that develop on carbonate rock. More specifically, it's a type of landscape formed when acidic groundwater dissolves soluble carbonate rock. This is known as dissolution, and dissolution creates a network of caves underground. Florida is one of the most karstic states in the United States. However, the karst in Florida differs from other karsts within North America and is distinguished as an eogenic karst, meaning it's geologically young. Its most distinguishing factor is that its limestone retains significant primary porosity and permeability. The porosity of Florida's karst is around 30 to 40%, which in comparison to other regions and their karsts, porosity can average around 2 to 3%. To understand further the karst environment within Florida, a brief discussion on its geological history is important. The basement rocks present in Florida differ in origin than the rest of North America. Florida originates from the landmass Gondwana, comparatively to Laurentia in North America, and sutured to North America during the formation of Pangaea. Soon after Pangaea formed, the supercontinent tore apart, and Florida was left anchored to North America. North America drifted away from the other land masses, and waters from the forming Atlantic Ocean flooded the basement rocks within Florida. The waters were shallow, and evaporation of the shallow water resulted in thick deposits of salt and gypsum. By the Cretaceous, these evaporates gave way to a massive deposition of limestone, and limestone deposition was stable through much of the Paleogene. The massive deposition of limestone dwindled within Florida as erosion from the Appalachian Mountains covered the platform within sediments. The focus region of the subject is the coastal lowlands of West Central and North Central Florida. The area discussed is bounded by the Suwannee River in the north and Tampa Bay within the south. Most of the caves and springs, not including the Miami region, developed within the Paleogene. These Paleogene-age limestones comprise the Floridian aquifer. The two significant formations within the Floridian aquifer are the late Eocene Okla limestone and early Oligocene Suwannee limestone. These two stratigraphic units are directly associated with most karst features within the Floridian aquifer. This is especially the case where the aquifer is unconfined. The research explores underwater and air-filled caves and the impact of changes in sea level on the karst environment, as well as distinguishing geological and hydrological characteristics of the karst environment within Central Florida. This study focuses on the coastal lowlands of West Central and North Central Florida. This includes the cities of Brooksville, Ocala, Gainesville, and Lake City. These are the areas in which Eocene and Oligocene limestones are exposed to the surface or only thinly covered by younger sediments. To help understand how these caves were formed, stratigraphic units of the Floridian aquifer were analyzed, deriving from drilling wells. A core sample was drilled and logged at Raider Hill in Citrus County, which provided data on the lithology, sequence stratigraphy, and permeability of the limestone at depth. Cave exploration and detailed surveys of air-filled caves at various locations helped reveal information on the passages and levels of passages within the area, as well as periods of stationary sea levels. These cave surveys mapped passage dimensions and elevations across many caves, including Brooksville Ridge and Warren Cave. Rose diagrams were used to determine the preferred cave passage orientations relative to the regional fractures. This information was collectively used to help define the distinguishing characteristics of the geology and hydrology of this region, as well as understanding the influence of sea level change on the karst environment. The image on the right is a rose diagram showing the orientation of all segments of the cave survey that was obtained from Brooksville Ridge. Additionally, methods of data collection analysis included the installation of water level and drip rate instruments in caves to help determine the hydrological responses of hurricanes and storms. This provided insight on how the Floridian aquifer recharges during large storm events. Hydrograph analysis was used to compare eogenic and telogenic karst hydrology. Information provided by monitoring water levels during summer season and severe storms helps distinguish the eogenic characteristics of the Florida aquifer in comparison to other karsts. The image on the left is a histogram of elevations relative to the survey passages within Brooksville Ridge. It demonstrates spot elevations and underwater caves and cavities and drilled wells. The results and key findings of this research concluded that caves organize along a paleo water table, and it cuts across geological structures. The elevation of these cave passages correspond to past sea levels. It was discovered that cave passage orientations revealed a preferred alignment along a set of northwest-southeast and northeast-southwest fractures. Passages oriented along fractures tend to be low and wide. Changing sea levels greatly influence the formation of this environment. Air-filled caves throughout the Brooksville Ridge, for example, are consistent elevations from 3 to 22 meters above sea level. These levels correspond to known paleo-shoreline terraces. This was a time of sea level, when sea level was higher and stationary for the caves to develop at the water table. For the underwater cave systems, their passage levels cluster at 15 to 120 meters below the modern water table. This indicates a time of lower seas. And during the Ice Age glacial maximum, the global sea level was around 125 meters lower than it is today. The Florida Peninsula was twice as wide, and the coastline was 200 kilometers west of its present location. The now submerged caves and springs were once an air-dried filled caves in the center of the Florida Peninsula. As previously reviewed, the research indicated that Florida's limestone is characterized as an eogenetic karst. This means that the karst occurs in a modern, recent carbonate deposition environment. The limestone has an extremely high porosity and permeability. The climate characteristic of an eogenetic karst reflects low latitude locations and is near warm marine water. The geological climate distinctions are demonstrated by the hydrology of the Florida aquifer. And hopefully I say this word right, the evapotranspiration of rainfall is as high as 90% during the summer months. Rain and storm events do not display changes in water level, even during the rainy seasons. They show a smooth and longer period cycles. Large and frequent storms, however, including hurricanes, were the distinguishing events that changed the water level within the springs within the Florida aquifer. Within the unconfined Floridian aquifer, water levels were raised more than 2 meters. Due to the high permeability of Florida's limestones, the infrequent storms recharged the unconfined aquifer simultaneously in the caves over large distances. Due to the factor that paleo water tables are not horizontal, the paleo water tables are higher in elevation further inland. Cave levels that are either below or at modern water tables were shown to have multiple generations of passage development. This is shown to potentially be the case for some air-filled caves. These caves occur at elevations from 12 to 15 meters above sea level. However, they remain partially flooded. Multiple generations of passage development is shown in deep underwater caves, which explains their greater size. A paleo water table was shown to move through different cave levels in conjunction with different sea levels. Water tables can reoccupy zones dissolved by previous water tables, and this results in the water table being able to pass through caves further inland and at a higher elevation. This can be seen near the Cody Scarp and Brooksville Ridge. Additionally, at Finch's Cave in Marion County, the modern water table has occupied a cave passage 15 meters above sea level. The image shown on the right demonstrates the porosity of the upper Floridian aquifer in west central Florida. The image is a geological cross-section that shows how the Floridian aquifer was shaped by changing sea levels over millions of years. It shows how the underwater caves were once at the water surface. The dashed lines represent the paleo water tables, and it shows that cave passages were formed at or just below the water table. This resulted in the stacks of cave passages formed at different depths shown within the image. What might be the implications that the karst environment has on Florida? Well, rapid urbanization within Florida has been happening since 1950 and has affected the amount of groundwater consumption. 90% of Florida's rely on groundwater. The majority of water used comes from the upper Floridian aquifer. Currently, water quality within the springs in Florida is on the decline. This includes nitrate levels being increased as a result of anthropogenic pollution, aka fertilizers, and chlorides and sulfates are increasing along the coast where saltwater intrusion occurs. The change in water chemistry at Florida Springs hurts species diversity and is the primary cause of toxic algae blooms. Florida Springs attract over 1 million visitors, and major bottling companies including Nestle, and Coca-Cola rely on Florida spring water. This creates a huge economic incentive to protect Florida's spring water's quality. The implications that this has on Florida does not stop here. Increased pressures for developable land and greater groundwater withdrawals has led to an increase in sinkhole collapses. Events such as sinkhole collapses has created more than $100 million in structural damages in Florida since 1997. This, in turn, increases insurance premiums in conjunction with hurricanes and flooding. Insurance companies have been ceasing homeowner policies. The occurrence of sinkhole collapses due to the karst environment present in Florida has led to an increase in engineering firms, environmental consulting companies, and law offices in the event of sinkhole collapses. Most sinkhole damages occur from cover subsidence sinkholes, in which subtle structural damages occur that are only detectable through physical methods such as seismic techniques and electrical resistivity. Cover subsidence is when sandy soils gradually migrate into karst voids, causing the ground to settle, and it affects things like uneven foundations, doors that won't close, and cracked walls. In conclusion, Florida's karst formed in Paleogene limestone, and cave passages hold a geological record of sea level history. Air-filled passages reflect a time of high and stationary sea levels, whereas submerged passages correspond with the last glacial maximum and low sea levels. Passage orientation has also shown to form along fracture zones within Florida. In west central and north central Florida, the karst is eogenic, meaning it has an extremely high porosity and permeability. This vastly differs from other karst systems in North America. The Floridian aquifer is recharged not by the rainy season, but large, infrequent storms such as hurricanes. The karst environment present within Florida presents a risk for Florida in the cases of spring pollution and sinkhole collapse. These hazards are driven by the usage and reliance on the aquifer systems, urbanization, and agricultural runoff. Florida's karst environment is a fascinating and beautiful geological environment present within Florida.